This video demonstration will discuss the setup and operation of the combined loading apparatus for Engineering 151 Strength of Materials. There are 4 of these setups, so the students can be broken up into 4 groups and work as a team on this particular exercise. First, I'll go through the setup of the apparatus. The setup will be almost identical for the other 3 systems, only minor differences between the different apparatuses. To start off with, the beam itself is housed between 2 2x4s and bolted to that just for mounting onto the table. We use a C-clamp with a plastic block on top to spread out the load across the top of those 2x4s, obviously clamped to the table itself. We have 2 strain indicators here. The reason we need 2 is we have 2 strain rosettes mounted on the beam. One on top called position A and one on the side called position B. Each of those strain rosettes has 3 individual strain gauges, so there are a total of 6 strain gauges. Each of these indicators has 4 channels, and so we have 3 gauges connected to one and 3 gauges connected to the other indicator. On the other end of the beam, we have an all-thread piece coming out of the other end of the beam where weights can be applied. Coming up from an eye bolt at the top, we have a key ring and a cable with hooks or loops on each end passing through a pulley. On the end of that cable, we can place a hanger. A second hanger is necessary because for one of the loading scenarios, a hanger needs to be placed at this location and also on the end of this all thread coming off the end of the beam. All of that is mounted on a lab stand with another C-clamp clamping it down to the table. We have a tape measure for the students because one of the critical dimensions that they need to measure is from the center of the eye bolt out to where the hanger is located. I try to make that the same. If you look at the results that I have documented and come with the lab handout for the TAs, that distance is 44.5 centimeters that I use, so if you want to make it the same, that'll make life easier as you check the setups for the students. The other critical dimension for the students is the distance from the strain gauges, again to the middle or center of the eye bolt. That dimension is what it is as the strain gauges are already fixed, and so is this eye bolt. That dimension will be very similar between the 4 different systems, but varies just slightly. One difference of some of the setups is you will find that this particular pulley is mounted with a piece of cable looped around. Some of them have an S hook that slides on like that. Also an S hook is used on the end of the all thread. So that's about the only difference between the systems. In terms of weights, the lab exercise requires 40 newtons of load, but in one of the scenarios, loading scenarios, you need 40 newtons here and 40 newtons here, so you'll need a total of 80 newtons per station. I'll talk a little bit about the strain gauges themselves. As mentioned previously, there are 2 rectangular strain rosettes mounted on the beam. Each of those rosettes containing 3 individual gauges. The first rosette is referred to as rosette A, and the second, which is on the side of the beam, is referred to as rosette B. When connecting to the strain gauge indicators, it's important to point out that it's nice if the connections are made in the same manner between the 4 different systems. And what I mean by that is, take for example the strain gauge on the top of the beam, that is gauge A, rosette A that is. The gauge that runs in the longitudinal direction records or gives the strain value epsilon sub A. The strain gauge running at a 45 degree to that is epsilon B, and transverse to the beam would be epsilon C. So again, at point A, we have epsilon A, epsilon B, and epsilon C. Epsilon A, I connect to channel 1, epsilon B, channel 2, and epsilon C, channel 3. Again, that's useful for students as they are asking you for help, and as you look at the numbers on the readout, you'll be expecting certain numbers in certain positions, and it'll just make it easier. For rosette B, again, epsilon A is measuring strain longitudinal, epsilon B is strain at a 45 degree to that, and epsilon C would be in this direction, transverse. Those values, again, connected to the second strain indicator, epsilon A at channel 1, and so on and so forth. It is, of course, important to balance out or zero the strain indicators before using them. Also, after zeroing them out, it's important to make sure that you place some weights on the end of the beam, take those weights off, make sure the values come back to zero so that the results that the students get are accurate. These strain gauges are delicate, and between setup each year in and out, we want to make sure that the strain gauges haven't been damaged, and that's one way to do it. As far as the lab exercise itself, it's composed of 3 different loading conditions. And within those 3 different loading conditions, there might be different weight values that are used for the loading. The first of the loading conditions would be pure bending. In that scenario, we place a weight at the end of the beam. Now, in addition to bending, it also will include a shear force in the beam as well, but we refer to it as the bending scenario. In this case, we'll take a hanger, place it on the eye bolt at the bottom of the beam, and weights can be added to that hanger. After doing so, of course, the strain values can be recorded off of the strain indicators. Students will be asked to place several different weight values and record those for this bending scenario. The second scenario is the torque-only scenario, and the torque-only scenario is probably the most complicated and can have the potential for giving values of strain that are off by the most, and I'll explain why that is. But first of all, to actually perform the torque-only condition, we first start by placing a weight on the end of the moment arm. So in this case, for example, I'm placing a 10 Newton weight at the end of that. I'll go ahead and pull this hanger off the bottom. I'm going to reinstall the pulley and run the cable through it, and the hanger on the other side. I'm going to take the same value of weight as what is at the end of the moment arm. Before I continue, I want to make sure that the cable that is attached to the keyring is vertical. So I'm going to check from this direction and check from this direction to make sure that the cable is in fact vertical. We want it to pull straight up. The reason we're doing this, if we apply just a weight on the end of the moment arm, that will in fact include a torque on the beam. But because of the direction of the weight, it will also imply bending on the beam, and we don't want that. So to counteract that bending effect, we're going to place an equal force but in opposite direction pulling up on the end of the beam. And the net effect is the torque only from that weight hanging at the end of that moment arm. So when the students need to calculate the torque, they're going to multiply the weight by the distance of this moment arm that they already measured. This particular scenario is subject to the most error because of the fact that we have friction between the pulley and this cable up here. One way to help with that is, after adding the weight, is to take and on the weighted side to pull down while I pull up on the cable that is attached to the beam, pulling down and then releasing. I find that if I need a 10 Newton force, after doing that little procedure, it comes closer to pulling up with 10 newtons. If you just take a 10 Newton weight and place it on this hanger because of the friction here and it's sticking, it probably will not be pulling up with 10 newtons. So again, you want to pull down on the weight while you pull up on the cable and then release until it finds equilibrium. That will generally help give you the most accurate value, combined with having a cable that is in fact vertical. Now, one way to know you're getting good values and have an equal 10 newtons here and 10 newtons here, for example, is to look at your strain gauge readings. The strain gauge readings for epsilon A and epsilon C, that is the strain gauges that run along the longitudinal axis of the beam and the transverse or perpendicular to the beam, those two values should be equal to 0 strain. And so as you're watching the students go around and make sure that they're getting values that are close to 0. If not, there's an issue here. 0 is perfect, of course, but the values realistically will go from anywhere 0 to 10 microstrain. So if they're under 10, I would say that that's fine. If it's over, I would have them do something different here, realign their cable, or try again with pulling down on this weight. Another thing they might try is taking all the weight off, re-zero their strain indicator, and then try it again. The final scenario is what we refer to as the combined loading scenario. Combined is referring to both bending and torque. Of course, with bending comes shear forces as well, but combined is referring to bending and torque. In order to do that, we just place a weight on the end of the moment arm, and again, as said previously, that will provide a torque or a moment that tends to twist the beam, but also that weight hanging out there will imply a bending moment on the beam as well.